Alright, so today we're going to be experimenting with a DIY buck converter. And the reason why I want to build a buck converter is so that I can put it onto this guy. This is our Arduino BMS, and the reason why I want to put a buck converter on this is so that I can control the amount of current that's going into the batteries. So because of that, I'm trying to build a simple buck converter that can be controlled with one of these blue pill boards or potentially on Arduino. I'll talk more about that in a minute. But anyway, this thing is quite simple. Essentially what I've done is I've taken the Wikipedia image for a buck converter. I've replaced the switch with a P-channel MOSFET. I added a 100 microfarad capacitor on the output. I'm using a 130 microhenry inductor, and right now I just have a really terrible, like 1 in 4,000 something rectifying diode, which is a terrible choice for something like this. I'm going to replace that with a Schottky here in a second. We'll see what difference it makes. Another thing I've done is I've added a ginormous input capacitor. That's this guy. I'm honestly not even sure that big capacitor makes any difference because I've done some testing already and I didn't really see much of a difference in performance with and without that capacitor. But anyway, it's on there. It's probably not that important. And the last and probably most important thing for my application is this ACS 712 sensor. So this is measuring the output current of this circuit. And right now I just have a dummy load, so this is a 10 ohm resistor technically, but because I've connected my alligator clip into approximately the middle of this resistor, it should be around 5 ohms, which allows me to pump a decent bit of current into it. So anyway, the rest of the stuff here, this is the power supply that I'm using to power the buck converter. So this thing is going to show our input wattage, and then over here I have the output current, the output voltage, and the output wattage. So having these two things here should give me a pretty easy way to measure the efficiency of the circuit as we try to make changes. Now I think the biggest thing that I'm going to be trying to tweak today is the PWM frequency that we're running this circuit at. So if we go back to that schematic that I found on Wikipedia, if we control the switch with PWM, we can effectively control the output current, which is exactly what I want to do because I want to create a constant current power supply for battery charging. And really, once this is set up in the Lithium BMS project, it would actually be pretty simple to be able to switch between constant current and constant voltage at will. Right now I don't even have this thing measuring the output voltage at all. I'm only measuring the current, and honestly I'm not even bothering to do all the math to figure out what the amount of current flowing through the sensor is. I'm just setting it at one constant analog value, whatever that analog value happens to be, and the value that the code in this guy shoots for is set off of this potentiometer. So for other measuring equipment, I have the oscilloscope over here. The top yellow trace is the gate of the MOSFET, so that's going to show us the on time of the MOSFET, and we can see what that waveform looks like. We can also see what the frequency is running at, and that bottom blue waveform is the output voltage, so we can see how much noise we have coming through the circuit. Alright, so another thing I do want to talk about before I start trying to tweak this circuit is going to be the reason why I think the blue pill board is going to be a better alternative to an Arduino in this case. The main thing is that this just gives you a lot more control when it comes to PWM than an Arduino does. So an Arduino gives you 8-bit PWM, which means that you can set your PWM values between 0 and 255. Now with an Arduino, your PWM frequencies tend to default to either 400 Hertz or about 900 Hertz. And that's what this does as well, unless you start to mess with the different timers and things, which I have done here. Now with an Arduino, the frequency maxes out at approximately, I think 30 kilohertz, which is about what I have this thing set to run at right now. Now this guy, instead of an 8-bit PWM resolution, it gives you a 16-bit PWM resolution. So instead of 0 to 255, you have like 0 to 6,500 and something. So this thing gives you much more precise control than an Arduino can. So we can't really use the full 16-bit PWM in order to drive a circuit like this because the frequency just isn't high enough, but we can drop the resolution, and we can drop the resolution so that it's still much higher than the resolution of an Arduino, and we can also get much higher frequencies than what an Arduino can drive. And that's exactly what I've done here. Right now it's set up to have a 10-bit PWM resolution, which gives you a range of values from 0 to 1023. So theoretically it allows for about 4 times more precise adjustment than you could get with an Arduino. It honestly has yet to be seen if that actually really makes that much of a difference, but the way that this is set up now is it hits around the 30 to 31 kilohertz that an Arduino would hit, but I actually have this thing dialed back. I can go much faster than 30 kilohertz and still maintain that 10-bit resolution. So anyway, let's go ahead and turn this on. Right now we're set at approximately the minimum amount of current, I think, and this thing is not really that accurate the way it sits. I think that's partially because of the fact that it's built up on a breadboard instead of being soldered and stuff, and there's probably a lot of noise being picked up in these really long wires that are going back to the analog inputs. And another issue that I think I have here is if you look at this blue trace, this is the output voltage, and it shouldn't have all of these spikes on it. That's not a good thing. And let me point out a couple more things with the oscilloscope. So for one thing, I have the frequency of the top trace, which is kind of jittering around, but it should be around 30 kilohertz. I have the negative duty cycle of this top trace, and then I have the RMS voltage of the output, which isn't really that important. What I do want to point out here is the fact that with this setup, because of the fact that it's using a P-channel MOSFET, when this is at a high voltage like this, the MOSFET is off, and when it's at a low voltage, the MOSFET is on, hence why this is negative duty cycle instead of positive duty cycle. So these little spikes where it comes down, that's actually where the MOSFET's on, not when the MOSFET is off. Now in theory, with a constant current setup like this, I should be able to adjust the voltage of our power supply and maintain roughly half of an amp out. So I just drop the voltage down a little bit, drop a little bit more. You can see it's not the most precise thing. We started at 16 volts, we're down at 12 volts now, and we're now around 450 milliamps. And you can see our output changing slightly on the oscilloscope there. And all the way down at 4 volts, we've dropped to like 250 milliamps, so it definitely doesn't have the most precise regulation. So let's go ahead and set our current limit up. We're going to try to get it to 1 amp. Another thing that I should mention with this thing is that the code that it's running is incredibly simple. All it is 2 if statements, and what it's doing is it's just reading the analog value from this thing, and it's comparing that to the set value that is coming from this potentiometer. And if the value coming off of this thing is lower than the set value, it's going to raise the duty cycle of the PWM and try to push more current through the system. And of course, vice versa is true as well. So if the value is lower, it's going to lower the PWM duty cycle, and it's going to try to push less current through the system. But anyway, let's just look at what we have right now. We have approximately 5.1 watts on the output, let's call it, and we have just call it 9.0 because it is jumping around quite a bit. We have approximately 52% efficiency, which is pretty terrible. A thing to look at on this scope here that I don't really even fully understand, it's quite hard to get this to trigger. It may actually be easier to get this thing to trigger on the falling edge. Yeah, it actually does look like it works a little bit better. But if I look at this, this is the MOSFET turning on. So it's relatively clean. It's got this weird little bump in it. I'm not sure what the deal with that is. But the MOSFET turning off is really, really slow, and it has this weird bump in it there. So that's probably part of the reason why I'm getting a bad efficiency. I think the other part of the reason though I'm getting bad efficiency is because this little diode right here. And why do I suspect that that's giving me bad efficiency? Well, because that diode is extremely hot. So let's go ahead and turn this off. And I'm going to replace that diode with something that should be a little bit better. So this guy is a 1N5820, which is a 3 amp Schottky diode. And I'll go ahead and shove this in the component tester, and we'll see if we can't get a reading on how much voltage drop this guy has. Forward voltage is only about 200 millivolts on this guy, according to this meter. Not sure what the datasheet values are for that, but I guarantee you 200 millivolts is going to be better than whatever this guy reads, probably around 0.7 or 700 millivolts, but we'll go ahead and shove this in here. This is one of those projects where the breadboard really doesn't work all that well for it because none of the components really fit into the breadboard because the leads are quite a bit thicker. And you could probably see, like on that diode, I had to solder some little some smaller component legs to it, and I've also had to do that with the inductor. But anyway, let's go ahead and test the old diode. And the old diode has a forward voltage of about 658 millivolts. So with the power supply back on, we're pushing more current than we were before. So let's go ahead and dial that back down to about the same level that it was when we were testing it with the other diode. So our output now, we're going to call it 5.5 watts. And our input is only about 7.5 watts. So just by changing out that diode, we've gone from approximately 15% efficiency up to about 73% efficiency, which is pretty acceptable. Now, one of the issues with this may very well be just the fact that there's so much noise in this. Even like that blue trace is the output voltage, and you can see how nasty that looks. That's not really a good thing. Now, there is a possibility that the frequency of 31 kilohertz is too high. But anyway, let's bump our current up a little bit. Take it up to about 2 amps. There we go, that's pretty much perfectly 2 amps. Let's call our output wattage about 20.7, and let's call our input wattage about 25.5, seems reasonable. So that gives me an efficiency of about 81%, which is pretty good. Let's go ahead and try to push a little bit more current through this. We should be able to hit 3 amps. Probably wouldn't want to go too much higher than 3 amps. All right, so that's all that we're going to be able to do right there, about 2.7 amps. And you can see that this is all that we're going to be able to do because this trace here just shows that our MOSFET is completely turned on. And of course, we're drawing about the same amperage on the input and the output according to the power supply on the meter here. So I think part of our efficiency loss is definitely because of the fact that it's running on a breadboard and it's running through a lot of really thin cabling and things like that. And of course, it's also running through the multimeter and everything else so that I can measure it. But our efficiency right now is only about 87%, and the MOSFET is just turned on at the moment. The MOSFET's actually getting quite warm, pushing 3 amps through it, which is kind of interesting. It shouldn't be that bad. But we can set our voltage up to about 20 with the way that the circuit is right now. So there's 20 volts. I'm going to back this down again. Change the range on the scope here so that's a little bit smaller and not in the way. Now let's try to get 3 amps going through it again. We should be able to do. Our input voltage and our output voltage are getting really close to each other. That's probably part of the reason the efficiency is coming up as I up the voltage. So there's about 3 amps. We have 46.7 watts out, let's call it. So 46.7 watts out and about 56 watts in, let's call it. That's about 83% efficiency. That's not too terrible. If you look at the oscilloscope now, you can see that our MOSFET is on for quite a bit of the time as opposed to off for most of the time. MOSFET right now is also quite warm, trying to drive 3 amps. And here's another thing showing you how the output regulation of this thing's not that great. I now have the potentiometer set at minimum again, and instead of half of an amp, we're pushing about 1 amp. So I think the next thing we're gonna try is lowering the output frequency, because theoretically lowering the output frequency is going to allow the MOSFET to not have to switch on and off as often. Theoretically, making it so the MOSFET doesn't have to switch as often means that the MOSFET's not gonna get as hot. All right, so I've changed the clock prescaler in the code from 2 down to 5. So that should slow our clock down quite a bit. Let's see where we're at. I do already notice that we have less of a spike in there, which is good. We're running at approximately 14 kilohertz, it looks like, which isn't bad. Yeah, about 14 kilohertz, so we've cut our frequency in half roughly by doing that. Another thing that's interesting about this is our initial current is now about 300 milliamps, which before I changed the frequency, it was about 1 amp. So that's quite a big difference. Let's go ahead and take it up to about 1 amp. 5.1 watts in, about 7.1 out, let's call it. Yeah, let's call it 7.0. It's kind of jumping around a lot. So that has an efficiency of approximately 72%. Let me also go ahead and change the range on this as well. So with the range changed on the output voltage, it doesn't look quite as clean. Also, I just realized the last time I tested the 1 amp, I was at 16 volts in, not 20. So let's go ahead and try that again. So dropping the input voltage by 4 volts dropped the current by about 80 milliamps, which isn't really that bad. So 16 volts in now, have about 5.2 watts out, 5.1 watts maybe. Let's call it 5.1 watts out, and about 6.7 watts in. Gives me an efficiency of about 76%, which isn't too bad. Let's go ahead and try it at 2 amps. 20 watts out and 23.9 watts in gives me an efficiency of 83%. Again, not bad. MOSFET is fairly cool right now. A little bit warm, but not bad at all. Let's go ahead and change our input voltage and just watch the oscilloscope. So you can probably see there how the negative duty cycle is going down as I adjust the input voltage up. Because with more voltage, you don't have to have that on time as high. But anyway, let's go ahead and take the voltage down and see what it does. Go ahead and go back up to 20 volts or so. And we'll crank her up to about 3 amps and we'll see what kind of efficiency we're getting. And you can see our nasty looking waveform starting to come back on channel 2. So that's not real great. So that is about 85% efficient. MOSFET is also getting just about as hot as it did the last time, so maybe that doesn't make that much of a difference. All right, so for an experiment, let's go ahead and just touch this probe somewhere on the resistor. And let's set it to about 1 amp. So that's about an amp and 5.7 volts. Let's move the probe back on this resistor. And we have about 0.97 amps and about 6.7 volts. Let's move it back a little bit further. And we have about 0.9 amps and 7.5 volts. So if we move it way up here, that gives me 1.2 amps at about half a volt. So that does demonstrate that this thing does at least attempt to regulate a somewhat decent constant current. But let's go ahead and make another change to the code and try to run it at a higher frequency and see what we get. So we're gonna go ahead and set this thing to run at the absolute maximum frequency that I can while still maintaining that 10-bit resolution. Turn this on, we should have a much higher frequency. You can already see all the noise in that bottom channel, which is not great. And you can see that the MOSFET really isn't even being turned on all the way, which also isn't great. And running, looks like approximately 60 or 70 kilohertz. Let's go ahead and try to give it some more current. And that cleans up the waveform so we can see it on the scope better at least. So we're running around 69 to 70 kilohertz it looks like. And that MOSFET is already unbearably hot. So 60 kilohertz is gonna be too fast for this thing in its current setup. All right, so let's go ahead and do one more experiment with this thing for today. And that's going to be to lower the frequency some more. So 3.5 kilohertz is giving us about 300 milliamps as a minimum current. Let's go ahead and try to run it higher. And now this is definitely in the audio range. You can hear the thing ringing. 3 amps flowing through it there. Let's call it 49.6 watts out and about 57 watts in. That's about an 87% efficiency, which is really pretty good. All right, take it back. Our frequency is not 3 kilohertz, it's about 7 kilohertz. And at 7 kilohertz, the switching of the MOSFET looks reasonably clean. And it's definitely still getting warm. It's not as warm as it was running higher frequencies, but it's pretty hot still. One thing I do notice about these lower frequencies is that you do see more ripple in that supply, which for my application doesn't really matter that much. The thing that I'm really more concerned about with is the ringing artifacts that are in here, and I'm not real sure how I can get rid of those. It could be something to do with the fact that this diode isn't being fast enough to respond to that, but I'm not really sure what causes that. I think the next thing to do with this may be to charge some batteries with it. Running it on a breadboard like this is kind of a hassle, and I think it would be worth it to go ahead and just stick it onto the Arduino BMS project because I've got plenty of space on that piece of perf board. The main thing that I've really learned here today is that the frequency isn't really impacting the efficiency of the circuit as much as I thought it was going to. And it seemed like the biggest impact that I'm going to have on efficiency is apparently going to be this diode and probably the transistor as well. I think another big upgrade to the circuit would probably be to use a proper MOSFET driver instead of an NPN transistor to turn the MOSFET on and just a resistor to turn it back off. Because you can buy proper MOSFET driver ICs that actively turn the MOSFET on and off and do so much faster than something like this would. But anyway, hopefully you guys enjoyed that video about playing with this little buck converter circuit. If you did, go ahead and click on the like button. If you want to see more content from this channel, go ahead and click on the subscribe button. And if you have any suggestions on how to improve the circuit, go ahead and leave those down below. Anyway, I'll see you in the next video, guys. Bye.